Today we are introducing a next-generation telemetry solution designed not only for competitive performance, but above all for the comprehensive management of a championship. The core idea is simple: to move from onboard telemetry limited to a single vehicle or team, to a comprehensive infrastructure capable of connecting all vehicles, teams and the organization to a single platform. This platform allows for the collection, analysis and utilization of data in real time, as well as the ability to remotely control systems through two-way communication. We designed this system to address three major challenges: on-track performance, operational safety, and the ability to comprehensively oversee a championship IMSA. In this presentation, we will structure our approach into 5 points. We will begin with the features offered from the user's perspective. We will then examine the system's overall architecture. Next, we will delve into the details of the onboard module. We will then discuss the platform's capabilities and its architecture. Finally, we will conclude with the business model and deployment details. Here is an overview of the features available from the user's perspective. The system's primary value is based on real-time telemetry. Each vehicle becomes a continuous source of data, capable of transmitting all of its critical parameters in real time: engine, power, chassis, and dynamic behavior. It also generates aggregated data from multiple sources, calculated in real time. Unlike traditional systems, this data is no longer limited to the pit or a local connection. It is accessible remotely in real time from anywhere on the internet network. This provides an instant view of the vehicle's condition on the track, but more importantly, it enables performances to be compared, analyzed, and understood as they happen. The benefit is twofold. For the teams, it is a tool for immediate optimization, adjustments, strategy, and understanding the vehicle's behavior. For the organization, it is a monitoring tool. The ability to track all participants, detect abnormal situations, and maintain a comprehensive view of the track. Finally, this telemetry forms the foundation for everything else: analysis, safety, remote assistance, and operational management, which we will discuss next. So far, we have viewed telemetry as a stream of data flowing from the vehicles. But the real breakthrough of the XAP system lies here, in its ability to interact with vehicles in real time. We are moving from a passive approach, observing, to an active one, monitoring and controlling. The system enables two-way communication. On one hand, vehicles continuously report their status, technical data, position, alerts. On the other, the control center can send information or commands directly to the vehicles. This opens up new capabilities for a championship like IMSA, centralizing the monitoring of all participants, immediately detecting a critical situation, transmitting instructions or alerts in real time, and, if necessary, intervening in the systems to ensure race safety. We are no longer simply talking about telemetry, but rather a digital marshalling system that complements traditional methods. It is a tool that enhances safety, responsiveness, and the consistency of race decisions. Once the data has been collected and is accessible in real time, the next step is to use it to improve performance. The XAP system does more than just display data. It allows you to organize it, compare it, and, most importantly, turn it into actionable insights. In practical terms, this makes it possible to analyze the performance of a vehicle, a driver, or a team during a given session, as well as to compare multiple sessions with one another. We can identify performance gaps, understand their causes, and adjust vehicle settings or strategy accordingly. This analytical capability is essential in competition, where gains come down to details: thermal management, energy consumption, and dynamic behavior. But it is also essential for organizing the championship. Furthermore, the tool can provide data in CSV format for analysis using other, more professional analytics software. It provides an objective and consistent view of performance, identifies anomalies or atypical behavior, and ensures overall fairness among participants. Finally, this data serves as a foundation for more advanced functions such as predictive maintenance or setup optimization, which we will discuss later. One of the system's key benefits is its remote technical support capability. In practical terms, each vehicle becomes accessible in real time to engineering teams, regardless of their location. This enables remote diagnostics to be performed with the same level of detail as if the engineer were physically present at the vehicle. In the context of a championship like IMSA, this opens up very concrete possibilities. An engineer can assist a team remotely during the race, analyze abnormal behavior, and propose corrective actions immediately. Since the data is accessible from any location, expertise can be centralized, skills shared, and the need to mobilize resources at every event avoided. This also significantly reduces response times. Where previously one had to wait for a post-race analysis or feedback from the workshop, it is now possible to understand and act in real time. This is a major shift. We are moving from a reactive model to a model of continuous distributed support. For the teams, this means improved performance. For the organization, it means greater robustness and technical consistency. Another key feature of the system is its ability to monitor not just a single vehicle, but an entire fleet or championship. Thanks to the platform, it is now possible to have a real-time multi-vehicle overview. All participating vehicles can be tracked simultaneously, along with their key technical parameters and operational status. This comprehensive overview also enables centralized team management. The organization can access consistent, structured, and comparable information across all participants, which is a key factor in a championship like IMSA. We are no longer limited to individual readings, but rather have true comprehensive monitoring of the championship. This allows us to track the technical progress of the race, identify trends, or detect abnormal situations across the entire field. Finally, the system incorporates automatic anomaly detection mechanisms. When behavior falls outside normal ranges, temperature, voltage, engine operation, and alert can be generated immediately. This enables faster intervention, improves safety, and ensures better technical control of the championship. In summary, we are moving from an individual monitoring approach to a comprehensive, structured, real-time oversight system. Beyond performance and monitoring, the system delivers direct value in terms of safety and operational efficiency. The first key feature is the ability to generate real-time alerts. As soon as a parameter falls outside the normal range, the system can immediately report the information without waiting for human analysis. This allows for a much faster response to a potentially critical situation. The second point is the continuous monitoring of critical vehicle parameters. Temperatures, voltages, engine operation, dynamic behavior, all of these elements are constantly monitored, allowing for the anticipation of deviations before they become incidents. This capability directly leads to the detection of technical incidents. The system does more than just display data. It identifies abnormal behavior, flags risks, and alerts teams or the organization. Finally, all this information converges toward a central objective, supporting in-race decision-making. Whether for a team or race control, having reliable, real-time, and structured information enables faster, more consistent, and better-informed decisions. In summary, the system does more than just observe. It ensures safety, issues alerts, and supports decision-making. This slide illustrates the monitoring interface used by a team manager, which serves as the central hub for real-time data analysis. The purpose of this dashboard, custom built by XAP, is to provide a comprehensive, concise, and immediately actionable overview of the vehicle's condition and its performance on the track. This screen can be customized to the client's specifications but is shared across an entire championship or team. On the left side of the screen are all the vehicle's key indicators. These include dynamic parameters such as engine RPM and speed, as well as essential operational data such as fuel consumption and critical temperatures. This information is presented as gauges and visual indicators, allowing for quick and intuitive reading without requiring complex analysis. The goal here is to immediately identify any deviations or abnormal behavior. In addition, more analytical data is also available, such as lap times, lap-to-lap variations, and information from onboard computers. This allows users to move from simple observation to a true understanding of the vehicle's behavior. On the right side of the screen, the track map adds a spatial dimension to the analysis. The vehicle's real-time positioning helps contextualize the data. This makes it possible to link a technical issue or a change in performance to a specific point on the track. This approach is particularly useful for identifying critical areas, analyzing racing lines, or understanding the impact of certain track conditions. One of the key features of this interface is its ability to centralize all information. The team manager has a unified view without having to switch between multiple tools. This enhances responsiveness and efficiency in decision-making. In a race context, this capability is crucial. It allows for anticipating technical issues, adapting strategy, or assisting the driver in real time. Finally, this interface perfectly illustrates the philosophy of the XAP system, transforming raw data into directly actionable information. It goes beyond simply displaying values to provide a decision support tool designed for real-world operating conditions. In summary, this interface enables the team manager to monitor, understand, and act in real time, with a level of information equivalent to that of being physically present at the vehicle. The engineering-oriented view, where the goal is no longer only to visualize data, but to perform a detailed analysis of vehicle data. On the left side, we see a time series representation of the signals coming from the vehicle. Several variables are overlaid, such as engine RPM, speed, pedal position, and certain parameters from the ECUs. This approach allows for the analysis of the vehicle's dynamic behavior over the course of an entire run. The primary benefit lies in the correlation between the signals. We do not look at isolated data points, but rather at the relationship between multiple variables, which enables us to understand the physical sequences and interactions between systems. For example, a change in engine speed can be linked to a driver action or a dynamic load. The temporal granularity also makes it possible to identify very short events that are invisible in an aggregated approach. This allows us to detect microevents, oscillations, or unstable behaviors. On the right-hand side, the circuit map adds a spatial dimension to the analysis. Each data point can be precisely located on the track. This enables a temporal analysis to be transformed into a geographical analysis. It also makes it possible to identify specific areas where behaviors occur: braking, acceleration, loss of traction, or thermal stresses. This dual perspective, both temporal and spatial, is essential for a nuanced understanding of the phenomena. It enables a shift from simple observation to causal analysis. Data engineers can thus isolate patterns, compare sequences, and identify behavioral discrepancies across multiple runs or vehicles. Furthermore, this interface allows data to be extracted for more advanced processing. The data can be utilized in external tools in the form of structured files to apply more advanced analytical methods such as statistical models or machine learning approaches, which Exact plans to integrate into its system in the near future. Finally, this approach forms the basis for the system's advanced features. In particular, it powers performance analysis, anomaly detection, and predictive maintenance. In summary, this interface does more than just visualize data. It enables the structuring, correlation, and interpretation of information to transform raw data streams into actionable insights for engineers. The race control interface serves as the championship's operational command center. The purpose of this interface is simple: to provide a comprehensive overview of all vehicles on the track from a single location, while enabling real-time interaction with them. On the left side of the screen is the list of competing vehicles. Each car is clearly identified by its number, the driver's initials, and their team. In addition to this identification, essential operational information is displayed: the number of laps completed, the fastest lap time recorded, and the current lap time. This provides an immediate overview of the dynamic standings and the relative performance of the vehicles. In addition, the interface highlights the current track sector and a predicted lap time. This information is particularly important because it allows you to anticipate performance even before the lap is over. This shifts the focus from a retrospective analysis to a forward-looking perspective. On the right-hand side, the track map allows you to precisely locate each vehicle. This real-time visualization is essential for understanding the context of events. In particular, it enables you to quickly identify critical situations, groups of vehicles, or potential incidents. One of the major benefits of this interface is the ability to interact with the vehicles. Race control can select one or more vehicles or even the entire fleet to send operational information. This information is displayed as digital flags. The list of available flags is directly accessible in the interface: yellow flag, red flag, safety car, or other specific instructions. This capability allows for the digital and instantaneous replication of traditional race management mechanisms. However, it offers a major advantage: speed and precision in dissemination. Information is transmitted directly to the vehicles, unambiguously and without delay. In the bottom right corner, the interface includes an event log. This log records all actions taken, including the sending of flags and their acknowledgement by the drivers. This traceability is essential. It ensures that the information has been received and taken into account. It also serves as a tool for post-event monitoring and analysis for the championship organizers. In an environment like IMSA, where the stakes are high and situations can be complex, this centralized supervision and communication capability is crucial. It improves safety, streamlines incident management, and ensures overall consistency in race decisions. In short, this interface does more than just display data. It serves as a powerful tool for managing the championship, enabling users to monitor, understand, and take action in real time with unprecedented precision and responsiveness. This slide illustrates a major shift in race operations management: the transition to real-time marshalling, supported by two-way communication. Historically, race management has relied on human and visual systems: track marshals, physical flags, and radios. While these systems remain essential, they nevertheless have limitations in terms of responsiveness, precision, and overall coordination. The system we propose introduces a new digital operational layer to complement and enhance these mechanisms. At the heart of this architecture is race control, which provides centralized oversight of the entire race. It has a real-time view of all vehicles, their positions, and their statuses. This allows for the immediate detection of any abnormal situation, incidents, slowdowns, or atypical behavior. This detection capability constitutes the first pillar of the system. The second pillar relies on real-time data transmission from the vehicles. Telemetry data provides a precise and continuous view of the situation on the track. It feeds automatic alert mechanisms which identify events without waiting for human intervention. This approach enables a shift from a reactive to a proactive approach. The third essential pillar is the ability to communicate down the chain of command. Race control can send instructions directly to the vehicles. This includes alerts, safety instructions, or operational information. This communication is immediate, targeted, and unambiguous. It eliminates the delays and uncertainties associated with traditional systems. Together, these elements form a complete loop. Data is fed up from the field, analyzed in real time, and then actions are sent back to the vehicles. This closed loop is the heart of the system. It enables much finer and much faster coordination of operations. In practical terms, this translates into several major benefits. First, a significant improvement in safety. Incidents are detected earlier, instructions are disseminated more quickly, and drivers have clear and immediate information. Second, the ability to react instantly. Race control can intervene without delay, adapt instructions, and manage dynamic situations much more effectively. Finally, centralized control of the entire race. The organization has a comprehensive, consistent, and real-time overview, enabling it to make informed decisions. In a championship like IMSA, where operational complexity is high and safety stakes are critical, this approach represents a transformative shift. It does not replace existing systems but complements them by adding a digital layer that significantly boosts their effectiveness. In short, we are moving from a primarily visual and local marshalling system to a connected global and real-time marshalling system. It is this transformation that enables us to simultaneously improve the championship's safety, responsiveness, and operational control. We will now go into detail about the features of the device itself. This slide describes the system's overall architecture. We have deliberately chosen an architecture that is simple, robust, and suited for global deployment. It is based on three fundamental components. The first is the onboard telemetry unit. It is installed on the vehicle and serves as the system's entry point. It collects data directly from the vehicle's communication buses and electronic systems. The second building block is 4G communication. This choice is essential as it allows us to leverage an existing infrastructure available worldwide. For a championship like IMSA, this ensures service continuity regardless of the circuit or country. The third component is the processing and monitoring platform. It centralizes the data, processes it, and delivers it in a format that is actionable for the teams and the organization. This architecture offers two major advantages. First, it is easy to integrate into any type of vehicle without requiring major modifications to the existing system. Second, it is scalable. It can manage everything from a few vehicles to an entire championship. It is this combination that enables a system that is operational, reliable, and deployable on a large scale. This unit is a system designed specifically for motorsport environments, where demands are high in terms of performance, durability, and compatibility. Its primary function is to serve as an interface with all of the vehicle's systems. It connects directly to various communication buses and provides access to all information available within the electronic architecture. The unit is compatible with the main standards used in industry and motorsport: CAN, CAN-FD, J1939, LIN, TCP, IP, and Bluetooth. This compatibility allows it to be integrated into a wide variety of vehicles without being dependent on a specific architecture. Once connected, the unit performs intelligent data collection. This involves not just reading raw data streams, but selecting, structuring, and preparing the most relevant information for analysis. Finally, this data is transmitted to the cloud, where it can be analyzed and utilized by the teams and the organization. This unit therefore serves as the convergence point between the vehicle and the digital infrastructure, and it is what makes all the features we have presented possible. The third essential component of the system is radio communication based on the 4G radio standard. This choice is fundamental, as it allows the system to leverage infrastructure that is already deployed worldwide. For a championship like IMSA, this ensures coverage across all circuits without requiring any specific deployment. The system enables real-time data transmission when the network is available. However, it is also capable of operating in offline mode when connectivity is poor or temporarily unavailable. This capability is essential in a mobile environment, where network quality can vary depending on the area of the circuit. The system's robustness relies precisely on this ability to adapt to real-world operating conditions. The unit incorporates automatic reconnection mechanisms, allowing communication to be re-established as soon as the network becomes available again. At the same time, data recovery strategies are implemented. Information is temporarily stored on the module and then retransmitted once the connection is restored, ensuring that no critical data is lost. In summary, 4G communication ensures reliable, continuous transmission that is adapted to field conditions. The final component of the system is the data platform, which serves as the operational hub. It is this platform that transforms the data streams transmitted by the vehicles into truly actionable information. The platform's primary role is to ensure centralized data collection. All connected vehicles send their data to single infrastructure, providing a comprehensive, consistent, and unified view of the championship. The platform then processes the data in real time. The data is not simply stored, it is analyzed as soon as it is received, which allows for the updating of dashboards, the generation of alerts, and the immediate detection of abnormal situations. At the same time, all data is retained in a historical database. This allows users to review past sessions, compare performance, analyze incidents, or identify trends over time. Finally, this information is made available to users via a dedicated interface in the form of dashboards. This interface allows data to be viewed in a clear, structured manner, tailored to the needs of each user, whether they are part of the teams or race control. In summary, the platform does more than just store data. It centralizes it, analyzes it, and makes it directly actionable. Now that we've looked at the uses and benefits of the proposed system, let's have a closer look at each of its components, starting with the 4G modem. Let's now take a closer look at the heart of the system, the onboard telemetry unit. Its primary function is data acquisition, but it can do much more than that. The unit is designed to connect directly to the vehicle's CAN buses, including multiple buses in parallel. In the current configuration, it can handle up to 3 CAN buses simultaneously, covering the entire vehicle's electronic architecture. This means we can access all available information, whether it comes from the engine, the electrical system, the chassis, or auxiliary systems. The unit then allows us to read all vehicle variables. We are not limited to just a few signals. The goal is to be able to leverage the full richness of the data available in the system. To achieve this, we integrate DBC files, which describe the structure of CAN messages. This integration enables reliable and consistent data decoding and the reconstruction of physical variables that teams can use. Finally, the system is fully configurable. Each application can precisely define which data should be collected, at what frequency, and in what format it should be transmitted. This flexibility is essential for adapting to different vehicle types and the specific needs of teams or the organization. One of the XAP unit's key strengths is its ability to operate in a wide variety of environments. This is not a system limited to motorsports, but a platform capable of interfacing with numerous industrial standards. The unit primarily supports CAN and CAN-FD buses, which form the basis of modern automotive architectures, as well as LIN for embedded subsystems. It is also compatible with the SAE J1939 protocol, widely used in commercial vehicles, trucks, and agricultural machinery. This allows the system's use to extend far beyond competition vehicles. We also integrate protocols such as Modbus, used in building automation and industry, while NMEA support enables connectivity with marine and navigation applications. Finally, the unit features comprehensive network interfaces including TCP, IP, Ethernet, Wi-Fi, and Bluetooth. This diversity of protocols makes it possible to connect virtually any type of equipment, whether embedded, industrial, or stationary. In summary, the device acts as a universal gateway between different technological worlds. This multi-protocol capability is a key feature, as it ensures the system's longevity and its ability to adapt to a wide variety of uses. This slide complements the data management logic by introducing an additional dimension, embedded processing. As mentioned earlier, the system allows users to select the necessary data via the software, ensuring that only relevant information is transmitted. It also allows users to configure the acquisition frequency, with rates of up to approximately 10 Hz over 4G, depending on operational needs. The unit always has an internal buffer, allowing data to be stored for approximately 48 hours, thereby ensuring data continuity even in the event of a network outage. But beyond these functions, the system now incorporates onboard computing capabilities. The device can perform mathematical calculations on aggregates directly at a source. This means it can generate summary metrics, averages, derivatives, or simple analyses without waiting for server processing. This approach offers two major advantages. First, it reduces the amount of data to be transmitted, and second, it provides information that can be used directly in real time. Finally, the system incorporates delayed transmission strategies. In the event of a network outage, data is retained and then automatically retransmitted once the connection is restored. In short, the device does more than just collect and transmit data. It selects, processes, and secures the data as soon as it is acquired. This control unit feature enables intelligent and secure communication management. The system is designed to prioritize critical data. Essential information can be transmitted in real time to ensure maximum responsiveness, particularly during races or in the event of a malfunction. At the same time, more detailed data can be stored locally in the unit. This ensures a high level of precision in the information retained without unnecessarily overloading the network communication. This data can then be automatically synchronized with the platform as soon as communication can permit. The system also relies on two-way communication. This means that it is not limited to sending information upstream. The platform can also send data or commands to the vehicle. Finally, all exchanges are secure. Communications are encrypted and rely on certificate-based authentication mechanisms, ensuring data integrity and system protection. In summary, the system combines three essential elements: data prioritization, robust communication, and a high level of security. It is this combination that ensures reliable operation in critical environments such as motorsports. This final feature introduces a key aspect of the system: the ability to control it remotely. So far, we have seen how the unit collects, processes, and transmits data, but it also allows you to interact with the vehicle. The first capability is modifying parameters or sending CAN messages to the display or the ECU. It is possible to adjust certain settings directly remotely without physically accessing the vehicle. This improves responsiveness and allows the system's behavior to be adapted to racing conditions. The system also allows for the triggering of scripts. This means that predefined actions can be executed automatically or on command depending on specific scenarios. This makes it possible to automate certain operations or react quickly to identified events. The unit also includes onboard diagnostic functions. It is possible to query the system remotely, analyze its status, and identify any malfunctions without disassembly or returning the vehicle to the workshop. Finally, the system allows for remote updates of the software and security certificates. This ensures that the devices remain up-to-date, secure, and operational throughout their life cycle. In short, this capability transforms the system. We are no longer limited to monitoring vehicles. We can also provide them with information, maintain them, and update their systems remotely. Now that we've looked at the uses and benefits of the proposed system, let's take a closer look at each of its components, starting with the 4G modem. Here, we'll take another look at the monitoring platform, but this time from the perspective of its practical use. The entire system is based on a centralized web interface. This means that all users can access the data from a standard web browser without any special installation, regardless of their location. This interface allows for the creation of multiple customizable dashboards. Each user can have a view tailored to their needs. An engineer can monitor detailed technical parameters, while race control can have an overview of the entire championship. The system is designed to be multi-user. Multiple teams, user profiles, and access levels can coexist on the same platform without interference. This is particularly important in an IMSA context, where different stakeholders must access data while maintaining clear separation. Finally, the platform includes role-based access control. Each user can be authorized to view, analyze, or act only on the elements that concern them. This ensures both data security and a clear organizational structure for operations. In summary, the platform offers a single, adaptable, and secure interface capable of meeting the needs of all championship stakeholders. This slide introduces the system's advanced analytical capabilities, which represent a key step in data utilization. The first feature is comprehensive data archiving. All collected information is stored over time, allowing for a precise reconstruction of a vehicle's performance over a session, a race, or an entire season. This historical database is essential for understanding phenomena, analyzing incidents, or refining settings. The system also allows for comparisons between different sessions. It becomes possible to compare multiple laps, races, or vehicles to identify performance gaps or specific behaviors. This capability is particularly useful for teams, but also for the organization in the context of overall championship tracking. Performance analysis then serves as a direct lever for optimization. The data provides a detailed understanding of how the vehicle operates and helps identify areas for improvement, whether technical or strategic. Finally, the system paves the way for predictive maintenance. By analyzing data over time, it becomes possible to detect deviations or early warning signs of failure and to intervene before a problem occurs. In summary, this analytical capability transforms data into a tool for understanding, optimization, and anticipation. This final functional component introduces a key aspect of the system: automation. The goal here is to transition from manual monitoring to assisted or even automated monitoring. The first level relies on configurable alerts. Users can define specific thresholds or conditions for the monitored parameters. As soon as a threshold is crossed or abnormal behavior is detected, an alert is automatically generated. However, the system goes a step further by automatically triggering actions. It is no longer just about alerting, but about reacting. Certain actions can be executed automatically based on defined conditions, sending notifications, modifying parameters, or activating specific functions. These mechanisms are part of operational scenarios. It is possible to define logical sequences tailored to situations encountered during testing or operation. Finally, the entire system operates under continuous monitoring. Data is analyzed continuously, without interruption, ensuring maximum responsiveness and immediate detection of events. In summary, automation enhances system reliability, reduces reliance on human intervention, and improves overall operational responsiveness. This slide presents an embedded IoT architecture that, despite its apparent graphical simplicity, actually reflects a particularly sophisticated systemic vision of vehicle infrastructure integration. It clearly illustrates XAP's strategic positioning, that of a player capable of mastering the entire value chain, from field data acquisition to remote monitoring in constrained environments. On the left, the embedded IoT module serves as the system's physical anchor. Built around an STM32 type microcontroller, it collects data from vehicle buses CAN, OBD2, and local network interfaces Ethernet Wi-Fi. This approach is fully in line with XAP's DNA, which is rooted in expertise with complex, interconnected embedded systems where robust data exchange is an operational imperative. The ability to interface with heterogeneous protocols is crucial here. It enables support for both existing internal combustion engine vehicles and electrified or retrofitted architectures. The core value then lies in secure transmission, enabled by the MQTT-TLS protocol. This choice is not arbitrary. It guarantees the lightness, reliability, and cybersecurity of data exchanges, three cardinal requirements in critical architectures. This represents a break from traditional embedded systems, which have historically been closed, and marks a shift toward a controlled, open approach to the cloud. The right side of the diagram illustrates this increase in abstraction. The sovereign cloud infrastructure, built around modern building blocks, Kubernetes, secure APIs, real-time monitoring, enables the processing, storage, and utilization of data. It offers high availability and elasticity, which are essential in industrial or competitive contexts where service continuity is non-negotiable. This approach aligns with the developments described in the XApp catalog, where systems are no longer mere devices but interoperable and configurable platforms. Finally, the application layer, rules, alerts, web interfaces reflects the system's operational purpose, transforming data into decisions. This is where differentiation comes into play. The user no longer merely receives information but gains the ability to analyze and anticipate, based on configurable rules and continuous monitoring. This architecture should not be viewed as a mere technical diagram, but as the expression of a strategic shift, that of embedded electronics becoming intelligent, connected, and remotely controlled. It positions XAP not only as an equipment manufacturer but also as an integrator of critical systems, capable of addressing today's challenges in mobility, energy transition, and technological sovereignty. For integration into a championship such as IMSA, the system was designed to be compatible with existing systems. It does not require any overhaul of current team or vehicle architectures. It integrates seamlessly, connecting to existing buses and infrastructure. This approach ensures a gradual, seamless adoption. The system also integrates into the team's workflow. Engineers can continue to use their tools and methods while benefiting from expanded access to data and monitoring capabilities. The goal is not to replace existing tools, but to enhance them and connect them to a comprehensive platform. Deployment is designed to be rapid. Installing the unit, configuring it, and putting it into service can be done in a short amount of time, allowing for rapid deployment during a championship. Finally, the system is adaptable to the specific constraints of the championship. Whether it involves technical rules, communication limitations, or organizational requirements, the platform can be configured to precisely meet the IMSA framework. In summary, the system is not only high performance. It is designed to integrate easily, quickly, and efficiently into an existing environment. Let's now turn our attention to the financial model. The approach we have adopted is intentionally simple and scalable. The goal is to provide a clear model that can be adapted to the size of the championship and is capable of evolving over time. This model is based on four main components. The first is hardware. This involves the acquisition of onboard telemetry units which serve as the system's entry point on the vehicles. The second component is the license. It provides access to the monitoring platform, analysis tools, and associated features. The third component concerns connectivity. It covers costs related to data transmission, particularly via 4G networks, as well as access to cloud infrastructure. Finally, the fourth component encompasses services. This includes integration, configuration, technical support, and operational assistance. This structure clearly distinguishes between initial investment costs and operational costs. It also allows the model to be adapted to the specific needs of the championship or the teams. In summary, we offer a transparent, modular, and scalable model consistent with an IMSA scale deployment. The first step is purchasing the telemetry module. This module serves as the technical interface between the vehicle and the platform. It enables the collection, processing, and transmission of data. It costs approximately €2,200 for the IMSA. The second step is integrating the module into the vehicle. This step involves connecting the unit to existing systems, particularly communication buses, and adapting it to the vehicle's specific architecture. Its complexity may vary depending on the configuration, but it is designed to be quick and non-intrusive. The quote will be provided by CMS. The third step is commissioning. It includes system configuration, registration on the platform, and verification of proper operation. It is at this stage that the device becomes fully operational. The quote will be prepared by CMS and XAP. Finally, this phase also includes maintenance and update licenses, generally 10% of the purchase cost, i.e., €220 per year. These ensure the system is maintained over time, particularly in terms of support, software updates, and security certificate renewals. In summary, this first component covers the entire initial deployment, from physical installation to the system's full operational launch. The second component of the financial model concerns the platform license. It provides access to the software infrastructure developed by XAP. The first element is access to the platform itself. This includes all data collection, processing, and reporting services, accessible via a secure web interface. The license also provides access to dashboards and analytical tools. Users can view data in real time, analyze historical data, and perform comparative or performance analyses. Another important aspect is fleet management. The platform allows for the simultaneous monitoring of a large number of vehicles, the organization of data by teams or categories, and a comprehensive overview of the championship. Finally, the license includes user rights management. It allows you to precisely define who can access which data and with what level of interaction. This ensures security, confidentiality, and a clear organization of responsibilities. In summary, this license is not just simple software access. It provides access to a true data management system that provides structure for the entire championship. The third component of the financial model concerns subscriptions, which cover the system's operating costs. The first element is 4G connectivity. Each device is equipped with a SIM card that enables data transmission. This subscription covers access to mobile networks and ensures communication between the vehicles and the platform. Generally, it is the championship operator or the user who obtains the communication SIM card. We can provide it, but it is not included. The second element is cloud access. This refers to the server infrastructure that enables the reception, processing, and redistribution of data in real time. This access includes the resources necessary for the platform to function properly, particularly in terms of availability and performance. It is priced at €20 per month per vehicle. The third point concerns data storage. All collected information is stored in databases, enabling historical analysis, comparisons, and in-depth analysis. Finally, the subscription covers real-time processing. It is priced at €20 per month per vehicle. Data is analyzed as soon as it is received, which allows for the updating of dashboards, the generation of alerts, and support for real-time decision-making. In summary, this component includes all the elements necessary for the continuous operation of the system. It transforms the infrastructure into an operational service that is always available and tailored to the demands of a championship. The final component of the financial model concerns additional services. These services enable the system to be tailored to the specific needs of the teams in the league. They are priced on a quote basis. The first element is the integration of vehicle systems. This involves assisting teams in connecting the unit to existing architectures, taking into account the specific characteristics of each vehicle. This includes, in particular, managing the various buses and electronic configurations. The second point concerns the definition and support for dashboards. The platform allows for the creation of highly customized interfaces, but this step may require support to structure the data and define relevant metrics. Configuring DBC files is also a key element. It enables the correct decoding of data from CAN buses and the reconstruction of actionable variables. This work is essential to ensure the quality and consistency of the information. Engineering support rounds out this package. It allows teams to benefit from technical expertise, particularly for data analysis, performance optimization, or resolving specific issues. Finally, monitoring or on-call services may be offered. Ils permettent de suivre continu de système, comme préférer de réaction de corps, avec opacité réaction rapide en cas d'incident. In short, these services enable us to turn a technical solution into genuine operational support tailored to the demands of the field. Beyond the cost structure, it is essential to understand the economic value delivered by the system. The first benefit is reduced maintenance costs. Thanks to telemetry and remote diagnostics, it becomes possible to identify problems more quickly, or even anticipate them, which reduces the need for major repairs and downtime. The second key factor is performance optimization. Data analysis enables improved settings, refined strategies, and the full realization of the vehicle's potential. This directly translates into a competitive advantage for the teams. The third point is the reduction of technical travel. Some analyses and diagnostics can be performed remotely, limiting the need to deploy on-site resources or return vehicles for inspection. Finally, the system contributes to improved overall reliability. By detecting anomalies earlier and continuously monitoring critical parameters, it reduces the risk of breakdowns and ensures more stable operation. In summary, the system is not just a cost, it generates measurable gains in performance, operational efficiency, and reliability. It is this combination that makes it a worthwhile investment at the championship level. Thank you for your attention. You can contact us at the following email address, contact@xap.fr. We look forward to seeing you on our channels.